This lecture is about unsupervised learning. We will see different typical unsupervised learning tasks and talk about unsupervised deep learning specifically.
Up until now, we have looked at so-called supervised learning tasks in which we trained neural networks on labeled datasets, that is, datasets which consisted out of such pairs of points where we had an input x and an output y, the label. In these supervised learning scenarios, we exploited the label information. This were usually class memberships in classification tasks or numerical values in regression tasks. And we used this information to train our algorithm. The model then learns a function that maps inputs x to outputs y. We saw different examples for such supervised learning tasks, like classification regression, or also object detection as shown here, or image segmentation as shown here. Now we will turn to a completely different learning principle, the so-called unsupervised learning. In the unsupervised learning scenario, the training data consists of unlabeled input points, x1 to xn. The goal is to learn the underlying hidden structure of the data. This sounds quite abstract, but what does it mean? We could learn some underlying hidden structure in means of clustering, performing dimensionality reduction, feature learning, or density estimation. We will explain what this is now. So the first example for unsupervised learning is clustering. Clustering is the task to find similar data points and to group the data in means of these similarity. So in this example here, we have some original data given where we know the labels, or we know which data point belongs to which group, here shown in different colors. This information of which group a point belongs to, so the label is not used by the clustering algorithm, of course, because we are in an unsupervised scenario. Then we see results of two clustering algorithms, k-means and the expectation maximization clustering, and we see that k-means does not find the groups correctly, so we have some of the points belonging to this group here classified as belong to this group here, but they in the original data they would rather belong to this big group. Also for this green group there are some misclassified or misgrouped points. We have better clustering result for the EM algorithm here, where we correctly find the groups of data, so the different clusters. Another example for an unsupervised learning task is dimensionality reduction. In deep learning, often referred to also as manifold learning, which we'll hear later about. So dimensionality reduction can be done for different reasons. For example, with the goal of projecting the data into a low-dimensional space that allows to visualize the data. So if we have some really high-dimensional data, it's difficult to interpret it. But if we project it in a 2 or maybe 3-dimensional space, we can better make a meaning of it. So here, for example, we could see that the data projected in a 2-dimensional space with something or an algorithm called principal component analysis, that the data consists out of 3 different groups, or we have different blobs of data, and we see that they all are rather spread in the y-axis than they are in the x-axis also. We could also use dimensionality reduction for compression. I think most of you heard about JPEG or so for image compression, but yeah, this reducing the dimensionality for data to have a compressed version of it is another reason for reducing the dimensionality. The third example is feature extraction or representation learning. If you might recall from the first lectures on supervised learning or feed-forward neural networks, one of the reasons to have hidden layers is that we can transform data which is not linearly separable into a feature space where it has nicer properties like being linearly separable. We could also imagine that one learns this kind of transformation from such a feature space, in a nicer feature space, in an unsupervised manner. This is especially interesting if we are in a scenario where we have a large unlabeled dataset, which is often the case because labels usually need people to assign the labels to the data, so there's a lot of handcrafting necessary. So it might often be the case that we have a large amount of unlabeled data and a smaller amount of data which is labeled and which could be used in a supervised fashion. In a scenario called semi-supervised learning, we combine this unlabeled data set and use it with this labeled data set and use the unlabeled data set to learn a good feature representation, and then use this learned feature representation for the supervised algorithm to learn a good separation or a good task on that. The fourth example was density fitting, as it was or is usually referred to in statistics, or as we often call it in machine learning, learning a generative model. Learning a generative model means that we learn the model of the data generating distribution. So we believe our data comes from a certain probability distribution, and now we have a machine learning model that models this distribution. Why do we want to do that? For example, if we can use it to generate data. In this example from this paper, we have we trained a network on a data set out of faces, and then we could sample from this distribution or the model and got new faces shown here. You can also use it for inpainting. So if you have examples like these images from Amnest, and you hide some part of the image, like here the upper part of the image, you can use the algorithm to reconstruct the rest of the image by sampling the missing values from the probability distribution given the not hidden pixels. Now we got a first impression on what unsupervised learning tasks are. Now we will briefly talk about what unsupervised deep learning is. So again, we are in a scenario where we have just unlabeled data points sampled from some data generating distribution, and unsupervised deep learning usually refers to either learning in so-called autoencoder, which is a special kind of neural network which is used for representation learning. Representation learning can again be used for feature extraction, dimensionality reduction, or manifold learning. Or deep unsupervised learning may refer to learning a generative model. This is, as we have seen in the last example, the task of learning a probabilistic model of the data generating distribution P data. If we have it, we can use it, as we have already seen, for data generation or for missing feature extraction, but we could also use it for outlier detection, reconstruction of images, denoising, or planning and reinforcement learning.